Okay, last page of our forces worksheet. We're now looking at component forces. We're getting into some really interesting stuff, and this is really gonna be just so cool when we start to apply it in real life, okay? So, our first problem, I'm actually gonna bring us all the way back to that lab that we did during the kinematics unit, where we tried to look at the acceleration of a pool ball going down a ramp. Now we used our total time and our total displacement to calculate that acceleration. But what we could do is we could use trigonometry to do the same thing. Because we've got a triangle, right? We've got a triangle, and we have a certain theta. We have a certain degree. Well, I know that this direction downwards is going to be 9.8 meters per second due to gravity. But I'm going to have a different distance going this way, parallel, a different acceleration going parallel to the ramp, and a different acceleration perpendicular to the ramp, okay? So those are the key terms we're using. So what we just did is we looked at the different sides of a triangle. What I'm doing now is I'm looking at the different sides of a force, okay? So let's calculate this out. And what I'm going to show you is there's a trick. So a miniature pool ball is rolled down a ramp with an angle of 10 degrees. What is the acceleration applied parallel to the ramp? What is the acceleration applied perpendicular to the ramp? If the mass of the pool ball is 0.02 kilograms, what is the force acting on the pool ball parallel to the ramp? So what is the actual force going down the ramp? So when we say parallel and perpendicular, we're saying we're splitting this acceleration up into our separate x and y. And our x is going to be based on the ramp's slope. So what's really easy to do in problems like this is to go, okay, well, I've got a vector, this y must be equal to this. So then my acceleration going down is actually my hypotenuse, right? But that's actually incorrect. Because what we're doing is we're taking a vector that's going straight down according to the Earth, and we're splitting it up into two separate components based on the ramp. One parallel to the ramp, one perpendicular to the ramp. So the easiest way to look at this is actually to draw the ramp sideways. Okay, take a little bit of thinking on my part. So that if we tilt that ramp up, so that the ramp itself is the flat surface in the x-plane, we'll call it x, and then we take the gravity, well now this is coming in at an angle here. Now the gravity, the acceleration due to gravity, is our vector. And that's actually how it works. This vector is going to split up into an x component going this way, and a y component going this way. So we can split that up nice and easily. We said theta is 10 degrees. So let's go ahead and use that. So this angle is 10 degrees right here. So then if we apply this same principle, and this being our hypotenuse, then this is going to be more what it looks like. This being our right triangle. So this degree right here, that is our theta. Okay? So what this is going to do is it's going to switch things up a little bit. Because if we just use this angle and assume that the ramp is everything, then we end up using a tangent and a cosine, and it doesn't end up with the right values. If we redraw a triangle right here with our theta at this point, then our sine, remember, it gives us the opposite. Our sine gives us parallel to the ramp. So sine of theta equals opposite over hypotenuse. Okay? So this opposite angle is going to be parallel to the ramp. So if I want to know the acceleration going down the ramp, I'm going to use sine theta times the hypotenuse of 9.8. Okay? So sine theta is going to be sine 10 times the hypotenuse of 9.8 equals the parallel side. So my acceleration as an effect of gravity, but not equal to gravity. Remember, we did this lab. We looked at this. 9.8 times the sine of 10. It's going to give me an acceleration of 1.7 meters per second squared parallel to the ramp. Okay? That's pretty cool. That's much easier, just doing one equation. So hopefully now you see the benefit of using the trigonometry. So let's go ahead and find the acceleration perpendicular to the ramp, the force that the ball is pushing into the ramp with. So we're going to do that by 9.8 cosine of 10, which equals, that's going to give us our perpendicular. And this is the sign for perpendicular, this is the sign for parallel, two parallel lines. It just helps you keep that stuff straight. And it's going to give us a value of 9.65 meters per second squared. So there, we've got two of our answers right here. And then the last thing we're being asked to find is what is the force acting on the pool ball parallel to the ramp? Well, we've got a mass of 0.02 kilograms. And force is equal to F equal ma. So, force is going to be mass, which is our 0.02 times our acceleration parallel, which is 1.7. 1.7. That's going to equal 0.03. So 0.03 newtons. And there we go. Let's take a look at the next one, where we're actually going to start applying these forces a little more specifically.